Hello, this is Mr. Collier, and today we're doing some modeling with linear, quadratic, and exponential models. Okay, in this first one here, we have a zoo charges $35 for an annual pass and $13 per visit. This looks like a linear model because we have a constant increase of 13 here. So we have an initial value of 35 and an amount of $13 extra per visit. So that's going to be linear with the y-intercept of 35 and the slope is going to be 13. So the equation for this, the function, is going to be c of x equals 13x plus 35. Okay, that's the function that models the cost. Select an appropriate domain and range in this context. Well, actually, the domain and the range, in this case, the domain is number of visits. So this can only be whole numbers. So the domain is, you could have 0 visits, 1 visit, 2 visits. There's a limit though, because we only have $145 to spend. So let's actually graph this and take a better look at what's happening. So I'm going to graph the function 13x plus 35. I don't need to see the graph. I know it's going to be linear. I'm just going to go to num so I can see what kind of y values pop out here, or what kind of costs are associated. So here we see 139 for 8 trips, but for 9 trips is 152. So this is the maximum. This is how far our values go. Okay, so for the domain it goes up to 8. You can, just make a list of all of them. And for the range goes from 35 is the minimum, and then the rest of the values are 48. I'm not going to write them all out now, I'm just going to write the last one. And all the way up to 139. But you should list them all if you want to write out the whole range. Okay, C of 5 is, well, you just substitute in x for 5. So we have 13 times 5 plus 35. And that, well, actually we can, if you don't want to work it out, you can just look at your table. That's 100. So that's $100. So that means it costs $100 for 5 visits. Next, c of x equals 110. That's like, this is not x equals 10, this is c equals 10. C equals 110. So we can plug that in here. 110 equals, and then 13x plus 35, and solve for x. So we get 75 equals 13x. X equals 75 over 3, which is 5.77. That means you can do 5.77 trips, which is not in the domain, so you can only do 5 trips. Okay, only 5 trips possible with $110. Lastly, we have the inverse. So the inverse, we reverse the x's and the y's. So this is not x anymore. This is actually c. So the question is asking you get the x value when c equals 113. So again, 113 equals 13x plus 35. Let's subtract 35 from both sides. Or actually, we can see this on the table. When the cost is 113, the number of visits is 6. So x equals 6. Okay? So $113 gives us 6 visits. Okay. Next example, this one's going to be exponential. There's 50 million kangaroos, and then there's 55 million. Find the percentage increase. You can probably see straight away that it's a 10% increase, but you can use the formula percent change equals new minus old divided by old, or original or something. So 55 million minus 50 million over 50 million. That will equal 0.1 if you do it in your calculator, which is 10%. So it is, oops, it's a 10% increase. Now, if it's going to be 10% every year, and we let t equals the time since the start of 2017, find an equation. So this is going to be an exponential model. It's called p to be the population of kangaroos. P as a function of time is going to be the initial value times 1.1 to the power of t. Okay, 10% is 0.1, but if you want to increase something by 10%, you do 100%, well, you basically have to do 110%, right? So this is equivalent to 110%. To increase by 10%, you multiply by 110%. Determine the year in which the population doubles. Well, doubles is going to be 100 million, right? Because the initial population was 50 million, so 100 million equals 50 million times 1.1 to the power of t. Solve that. Let's use our calculator. We can go to apps and type both of those in. So I think I have them ready. Here's the function, and here is 100 million. We just need to find the point of intersection. We can see it here already. That's an exponential function there in orange. Let's get the intersection, and it is 7.27. Okay, let me draw a sketch of that. We have that, we have that. The intersection is 7.27, comma 100 million, of course. 1, 2, 3, 1, 2, 3. So after 7.27 years, the question asks you which term of the year, so it's talking about the date, basically. So if you add 7 onto that, it's going to be in the year 2024. In the year 2024. Okay, next we've got C is the concentration of a medication over time measured in hours. Okay. All right, so we have a bunch of points. You can see the graph here. Scatter plot's already done right here. What's the best model for that? That looks like quadratic to me. Quadratic. It's not linear, it's not exponential. No, it looks like quadratic. So we're going to pick 3 points to make our own model. Now, if you want it to go through the vertex, you have to pick that, and don't pick 3 points next to each other. Points farther away would be good. So I'm going to pick A, G, and K. And we can substitute it in here and use our calculator to find A, B, and C. So I'm going to substitute all those points in. The first point is 0, 0. So I can substitute that in for X and Y. And I'm going to write A times 0 squared plus B times 0 plus C equals the Y value is 0 for the first one. And the next one is going to be, that's the maximum G, so that's going to be right there. That's A times 6 squared plus B times 6 plus C equals 15.03. And the last point is that, so that's A times 10 squared plus B times 10 plus C equals 8.26. And we can figure out the A, the B, and the C by using our calculator. Let's go to linear solver and type in the coefficients. In front of C, in every one of them, there's a 1, right? 1C. So you can put in a 1 for all of those zeros. You can literally type in 6 squared, or you can work it out in advance. You type in 6 squared and 10 squared, you get their values. So if everything is in there correctly, you'll get the A value is this, and this is the B value, and this is the C value. So our model is Y equals negative 0.420 if you round up 3 significant figures. X squared plus the B value is 5.02. 5.02x, and then plus 0 at the end. So this is our model. And let's actually, so in Desmos, let me turn this model off. That's what it looks like. So it goes to the maximum, and it goes through these 2 points here. It goes through the 3 points we picked, but it doesn't do so well with these points right here. So that's what the graph looks like. Now we're going to do regression, which is something on our calculator which you don't have to do on tests, but it's very useful if you want to model these things, like for an internal assessment or something. So to do this, we go to apps, 2 variable statistics, statistics 2 variable, type in all the data from our table, make sure it's correct, and then we click on this number called symbol. And you can choose wherever you want. You can choose exponential, linear, logarithmic. But obviously our data looks like a parabola shape, so we pick quadratic. If you don't see anything there, you gotta click plot and then go back to symbol. And there is our what we call the regression equation. The regression equation minimizes the distance between the curve and the points. So the equation is, to see it, you might want to click on it, and then you can see a bit better down here. So it is y equals negative 0.374 x squared plus 4.56x plus 0.121. So that's our regression model. Coefficient determination is called r squared. I'm going to show you where that is. So back where we put in the data, here under stats, you have r squared is 0.986. 0.986. Okay, so that's very close to 1. It's a good fit. Okay, close to 1, so it is a good fit for the data. Okay, sketch the models of the scatter plot. Well, let's take a look at Desmos, and here is the model, the regression model. You see it fits all the points very good, but it doesn't do a good job with the vertex. Okay, so that's what we can answer here. The regression model fits all points well. Okay, our model by hand fits the vertex better. So depending on what you want to use it for, one might be better than the other one. Use both models to determine when the medication will be fully absorbed. So that will be the maximum amount of absorption here. So we already have from our model it's going to be 15.03 because we go through that point. So our model. Then we have C, actually we have max equals 15.03 milligrams. And for the regression model, we can check out the maximum of this graph. Oh, sorry, it happens at, I think they want the x value here, 6.1 hours. So this is 6.1 hours. And for this one here, I think we needed the x value, so 6 hours. Because they're asking at what time, so after 6 hours, or 6.1 using our regression model. Can we use the model to determine the concentration after 24 hours? Well, no, because it only works up to 12 here. So maybe this actually, in actual fact, I think these kind of graphs, they kind of go off asymptotically later. So it looks like a quadratic at the beginning, but you need a different function to model the rest of it. So C of 24 is negative. So it's not valid.